Dear students, let's proceed with our lectures on the topic of tension processes in linear circuits with lumped parameters. Now let's consider an example of tension processes in RL circuits calculation. Why it is RL circuit? We have here only one reactive element, only one inductance, and it is Rayleigh branched in comparison with Rayleigh plane circuits that we have been considered previously, but it should be used the approach that I have explained you in the previous lecture. This approach says us that we can consider such a Rayleigh branch schematic as equivalent resistance which is connected to this inductance, and this equivalent R equivalent can be determined as equivalent resistance relatively clamps to which inductance is connected in the regime after commutation, and at replacing this active schematic by its passive equivalent. So we should replace EMF and current sources by their inner resistances. Inner resistance of EMF equal to 0. So for this we should just remove this circle, and we will have just short circuit. Remove, I mean mentally, of course. It's just approach which permit you to remember how to deal with inner resistances of EMFs and current sources. It will be just short-circuited part of schematic instead of this EMF when it is considered as passive, you see, and it should be considered in the regime when a commutation does happen. So let's consider processes before commutation, because it will be necessary for us to know IL from minus 0. So at t less than 0, we have here DC source. So for steady-state DC processes, inductance can be presented as short-circuited part of schematic, because this UL equal to L dIL by dt, and for steady-state DC processes, all derivatives equal to 0. So we have something like short-circuited part. This key was opened, and we can determine this current. Before commutation. We can calculate resistance of this schematic relatively clamps to which EMF is connected. It will be, you see, it will be this to R and this to R will be connected in parallel. Yes, it is like short-circuited place. It is absent. So this branch and this branch are connected in parallel. So the equivalent resistance will be 2R multiplied by 2R over 2R plus 2R for R. And you should remember that if two equal resistances are connected in parallel, their equivalent resistance will be 2 times less than resistance of each of these two parallel connected branches. So it will be just R, and these two parallel branches are connected in series with this R resistance. So equivalent resistance of this schematic will be equal to R plus R to R, and we can determine this current I1 in the branch in which EMF is connected as ratio between E and this 2R, I1 E over 2R. Then we can determine easily currents in these two branches. Yes, you see, as their resistances are equal to each other, it will be current here will be 2 times less than this current, so it will be E over 4R. Understandable? Or we may consider it, if this resistance will be equal, we can consider it with help of current divider rule. So this IL will be equal to I1 current which flow to these two parallel connected branches multiplied by resistance of the opposite branch I1 multiplied by 2R over sum of the resistances of these two parallel connected branches 2R plus 2R. So it will be 2R over 4R or 1/2 of I1. We have this IL, E over 4R. So we can write down that IL from -0 equal to E over 4R. After switching at t greater than 0, we can write down that IL current through inductance. Before, I have explained you earlier that this current, all equations should be write down relatively this current, because current through inductance will be source of natural components of currents of all other branches. So we should write all equations relatively this IL current, and we can write down that after switching IL will be equal to sum of IL forced plus IL natural. And after switching, after switching in steady state regime, as it is DC EMF, voltage drop across inductance at t tends to infinity, voltage drop here will be equal to 0, like in the regime just before commutation. So, but here we should consider schematic after this key is closed. And when its key is closed, this 2R resistance will be short-circuited. It will not participate in any processes, because if we have two parallel connected branches, resistance of one of which equal to 0, we will have equivalent of these two branches resistance will be equal to 2R multiplied by 0 over 2R plus 0, and it will be equal to 0. So it is just short-circuited part, and it is also short-circuited part in steady-state DC processes. So this 2R resistance will be also short-circuited by this path. You see? So we will have only this, we will have this part of current, okay? Because it will be, this resistance to R will be short-circuited by this branch, because in steady-state regime, inductance behaves as a short-circuited part of schematic. So it will be IL force will be equal to E over R. I1 will be equal to E over R and equal to IL, because it will be this path of current flowing, yes, and this inductance and this resistance will be connected in series. So the same current will flow through them. We can write down that IL forced equal to I1 forced equal to E over R. Okay, it's for t equal tends to infinity for steady state regime after commutation. Then natural component should be written as IL natural, the same form, integration constant A multiplied by exponent integral minus t over tau L, and tau L equal to L over R equivalent, okay, the same way as before. And R equivalent, we should determine relatively clamps to which inductance is connected for the schematic after commutation. So for schematic where 2R will not appear at all because it will be short-circuited after commutation, but this 2R will appear for the moment t greater than 0, for the moment when transient processes occur, because only in steady-state DC processes it will be fully, totally short-circuited, not during transition process. So we will have this E, which should be replaced by short-circuited part when we determine R equivalent, because R equivalent is determined for passive equivalent of the considered active circuit. And for this, we should replace this EMF by its inner resistance equal to 0. So it will be, you see, it will be short-circuited part, it will be R, this to R, and this L, not L, but terminals to which L is connected. You see, it is here, A, B, its clamps to which inductance is connected, then this to R, and this R. And it is rather easy to determine equivalent resistance relatively these clamps, because we have two resistances connected in parallel. Okay, so their equivalent resistance will be product of these two resistances R and 2R over their sum over 3R, 2R plus R. So it will be 2/3 of R. Tau L will be equal to L over R equivalent, L over 2R, and 3 will be in numerator. 1 over tau L, because we have here T over tau L, so 1 over tau L, it will be inversely proportional to this expression, it will be 2R over 3L, and therefore IL, current through this inductance, will be equal to sum of forced component is E over R, plus natural component. Natural component is this integration constant, but by E there will be minus T over tau L, and tau L is determined through this equivalent resistance relatively clamps to which inductance is connected. So IL equal to E over R first component plus this natural component. To determine this integration constant, we should use first commutation law, and we know that it is here, it is written first commutation law, yes, and we know that current before commutation through inductance was equal to E over 4R, yes, IL E over 4R, it's before commutation, and after commutation it will be equal to this expression at t equal to 0. So it will be at t equal to 0, this coefficient will be equal to 1 unit. So it will be E over R plus A. It is here. From this equation, we can easily determine A. It will be minus 3/4 of E over R. And so IL will be equal to first component, this first component, plus A, it minus 3/3 of E over R multiplied by E is minus T over tau L, or minus E is minus 2R over 3R multiplied by T. Its expression for current through this inductance. Let's stop on this, and in the next part of schematic I will explain you how to determine natural components of currents in other branches when we consider that this current is source of natural component of such currents in all other branches. Okay, so bye bye for now, and let's meet next lecture. Please don't miss it. Bye bye. Have a good